Hello everyone. Today we will conclude our discussion on thermoelectric effects and we will start a new and interesting topic, the topic on quantum dot devices. I'm sure you will be quite interested in this new topic. But before going into this, let's quickly review what we have seen. So what we have seen is that in the expression of the current, F1 minus F2 is the forcing function, and forcing function means that if this term is non-zero, in that case the current will also be non-zero, and F1 minus F2 depends both on voltage difference across a conductor and temperature difference across a conductor. So this lies at the root of the thermoelectric effects. In thermoelectric effects, broadly the thermoelectric effects are defined as the interconvertibility of heat into electricity and electricity to heat, basically, which means by a temperature difference we can produce a voltage difference and vice versa. So study of this phenomena, this interconvertibility of heat and electricity, that comes in thermoelectric effects, and in this sequence what we also need to consider is the notion of heat current, because what we have seen so far in this course is the notion of charge current, which is given by this expression, and that comes from the expression of the differential charge current. In heat current, we just need to replace Q by E minus EF in this expression, and that way we will obtain the heat current. And if we have a voltage difference of delta V and a charge difference of delta T, in that case the charge current, the total charge current in the semiconductor is given by this expression. I is G times delta V plus ST times delta T, and the total heat current is given by this expression, in which IQ, Q means now it is the heat current, is minus TL times ST times delta V minus K naught times delta T. And we have discussed about these two forms of current in our previous class. So that naturally brings us to what is known as Seebeck effect, which is the development of a voltage difference across a conductor when we have a temperature difference across its contacts. So what Seebeck effect says is that if one of the contacts is hotter as compared to the other one, in that case there will be an open circuit voltage. If the semiconductor is open circuited, we have not connected anything, and if we connect the semiconductor to an external electronic circuit, in that case this will supply a current to the external circuit. So it means that we are converting heat, essentially the temperature difference, to electricity. And what we saw was that the Seebeck coefficient can be defined as minus delta V, the voltage produced, as a function of delta T, the temperature difference applied when the current is 0 in a semiconductor, and this is given by ST by G. This comes from the Soret electrothermal diffusion, and G is the electrical conductance of the material. Okay. So this is what we have seen so far. A complementary thermoelectric effect is the Peltier effect. And what is Peltier effect? It is the development of temperature difference due to current flow in a conductor. Okay. And now we need to be very careful, because due to current flow the heat is generated, because the Joule heating appears because of the current flow, because of the scattering of electrons with the lattice atoms or in electron-electron scattering. But this is something different. This is when we force a current. So for example, if we have a semiconductor and TL1 is equal to TL2, which means both of the ends are at same temperature, and in this semiconductor if we force a current from contact 2 to contact 1 this way, which means that electrons will flow from 1 to 2, electron flux will be in this direction. In that case, a temperature difference will appear in this semiconductor, and this is known as Peltier effect, development of temperature difference due to current flow. And please also keep in mind that this is different from Joule heating, the I square R heating, and this will become clear as well. So, in other words, what we can say is that the Peltier effect is an effect whereby the heat is given out or absorbed when an electrical current passes across a junction of two materials. Okay? And in this case, initially the sample, the semiconductor is isothermal, which means the temperature is the same everywhere, and electrons, as electrons flow from left to right, they essentially carry kinetic energy, and what it means is that they carry a certain form of heat, or they carry heat in the form of kinetic energy from left contact to the right contact. What it means is that they absorb heat from the left contact and put it in the right contact. So, the left contact becomes cool and the right contact becomes hot, and that is how this temperature difference is created. So, let us also have a more I would say intuitive picture of this generation of temperature difference as a because of the current flow. So, we are taking an n-type material, this essentially this material, and the left contact Fermi level is EF1, the right contact Fermi level is now EF1 minus QV, because we are forcing a current from contact 2 to contact 1, and that is done by, most of the times that is done by applying a battery of positive terminal on the right contact. So, forcing a current from contact 2 means that the right contact is on a higher voltage. So, which means that the Fermi level on the right contact is now slightly lower as compared to the Fermi level on the left contact. Okay. So, this is how this heat is absorbed from the left contact and given to the right contact. We are assuming that the contacts are bulk materials where most of the times near equilibrium conditions prevail, as we assume in most of our discussion, and that's a fair assumption, because generally these contacts are metallic contacts and they have a lot of electrons. Also they are big in size, and that is why these near equilibrium thing is not, or near equilibrium assumption is not an invalid assumption. So, as all of us know that the electrons transport through the semiconductor in the conduction band. So, what needs to happen is that electrons, when there is a current from right to left, it means there is an electron flow from left to right. So, electrons need to jump from left contact into the semiconductor and then to the right contact. And if we take an n-type semiconductor, electrons essentially need to jump from here to the conduction band of the semiconductor. So, we are assuming that the current conduction happens at energy level ECX plus delta n. So, ECX is the bottom of the conduction band, but as all of us know from the modes that generally the number of modes in a bulk semiconductor right at the bottom of the conduction band is very low in number. So, the actual current flow happens slightly above the bottom of the conduction band, and this is the average energy at which the current conducts. So, it is the bottom of the conduction band ECX plus delta n, and this delta n is quite close to is few kT essentially. So, the current conduction in most of the semiconductor happens few kT above the bottom of the conduction band. So, essentially we need to, or the left contact needs to put electron in the semiconductor at this energy level ECX plus delta n, EC0 plus delta n essentially, because this is x equal to 0, and similar the right contact will take electrons from this energy level EC L2 plus delta n to its Fermi level. So, this is a more, I would say, a more magnified picture of the current conduction, and here we have only shown the left contact, also its Fermi function. So, as is clear that the Fermi function is a distribution function across the Fermi level, and the bottom of the conduction band of the semiconductor is above the Fermi level of the metal, Fermi level of the contact. So, the electrons that will go from the left contact to the semiconductor will be the electrons that are above this energy level. So, from the Fermi distribution function, the electrons in the tail of the Fermi function will jump to the semiconductor, okay? Because these electrons will see empty states right in front of them. So, what it means is that now the Fermi function on the metal, after these electrons have jumped into the semiconductor, this is disturbed from its equilibrium state. Now, the Fermi function is disturbed, and since this is a bulk contact and we always most of the times near equilibrium conditions are ensured, very quickly because of electron phonon interaction, because of the inelastic scattering in the contact, the Fermi function will attain its equilibrium value, its equilibrium shape essentially. So, what it means is that some electrons will essentially jump from below the Fermi level to above the Fermi level. So, what it means is that the semiconductor has taken high energy electrons into it, and these high energy electrons need to be replenished from the bulk. So, that way it is as if the semiconductor has extracted energy or the heat from the contact, and similarly on the right side these electrons will be given to the right contact. So, these high energy electrons are given to the right contact at a lower Fermi energy, at a lower Fermi level, and that way this heat, excess heat is given to the right contact and energy is dissipated on the right contact. So, energy is absorbed, a net energy is absorbed on the left contact and a net energy is given to the right contact in this way, because in this way this is like evaporation actually. That is a good way to understand this, because in evaporation what happens is that in a liquid, for example in water, high energy particles essentially evaporates that leave the rest of the liquid colder. Similarly, high energy electrons go to the semiconductor, to the n-type semiconductor, and then to the right contact, and this left contact becomes slightly cooler. Now, these high energy electrons dissipate this excess energy to the on the right contact, and this right contact becomes slightly hotter, and that way a temperature difference is created across the device from the left contact to the right contact, which means that a net heat current is also there in the semiconductor. So, because of an applied voltage, because of a current being forced in contact 2, there will be a heat current as well in the system, and that is essentially the underlying mechanism of the Peltier effect, which is the development of temperature difference due to current flow, which means that a net heat current is also produced because of an current flow in the system. So, now we need to understand the heat current, and the heat current is given by, if you remember from the last class, is given by this expression. IQ is minus TL ST times delta V minus K naught times delta T, and this is rewritten as this term IQ is minus pi times delta V by G minus K naught delta T. Delta V naught delta V by G is the current, the charge current in the system because of the applied voltage. So this becomes I, so that's why we can write it like this. And this pi is now, so V is equal to I times R, I by G, so I is V times G. So it should be, so please correct this, this should be delta V times G. So this becomes, so we need to divide by G, multiply by G, and in that case this pi essentially is TL times ST divided by G, and ST by G is the Seebeck coefficient. So this is TL times Seebeck coefficient. So pi is known as the Peltier coefficient, and what is the Peltier coefficient? It is the lattice temperature times the Seebeck coefficient. And in other words, what it means is that if there is no temperature difference, that we do not apply any temperature difference, we take an isothermal conductor. So if this delta T is 0, in that case pi is, or the Peltier coefficient is essentially the ratio of the heat current to the charge current essentially at delta T equal to 0. So this is the definition of the Peltier coefficient. And as you might have already guessed, the Seebeck coefficient or the Seebeck effect and Peltier effect are in a way complementary to each other. Seebeck means development of a voltage difference because of an externally applied temperature difference, and Peltier means development of temperature difference because of the current induced in the system. So, these two are the I would say the building blocks of, or these two are the central concepts on thermoelectric effects, thermoelectric devices, and most of the thermoelectric devices are based on these two principles, these two effects. So I hope you would be able to understand, if you come across any thermoelectric idea, you would be able to understand from these basic concepts that we have discussed so far. So in conclusion, what we can say is that always the electric current, the charge current and the heat current are accompanied with each other, and both of them depend on the applied voltage and applied temperature gradient in the system. I would also like to say that, just to sort of remind you, that the Peltier, this temperature difference due to current flow, this is different from Joule heating, because now this heat, IQ means heat generated in the system, is directly proportional to I. So the Peltier heating is directly proportional to I, and Joule heating, which comes from the scattering of electrons with the lattice, is proportional to I square. So that's a central difference. That's, please keep in mind, but the origin of Peltier heating is from can be understood from the Fermi distribution on both sides, as we understood from this particular diagram, that high energy electrons are taken from the left contact and put into the right contact. That's how heat is absorbed from the left contact and given to the right contact. And as you can see that this kind of heat transfer is reversible as well. So if we change the direction of the current, the direction of heat current will also change. The Joule heating is not reversible, it is irreversible thing. So in conclusion, there is always, we need, while considering the charge current and heat current, we need to consider the effect of both voltage applied and temperature applied, and these currents, these coefficient in these current expressions are given by these expressions. This we have discussed already, just put to, we have just put them to keep everything at a single place. And this idea, this discussion can be extended to a 3D bulk case as well, which is essentially the diffusive transport case. And a 3D bulk case, these equations will get modified in this way. This will be the charge current density, this will be the heat current density, and the Sauret coefficients and this K coefficients will change. These are the bulk analog of ST and K naught, and these are the corresponding expressions. So I would recommend all of you to go through these expressions. These are just the natural generalizations of the derivations that we have already done. Okay. So this essentially concludes our discussion, this completes our discussion of thermoelectric effects. We have not gone into the details of thermoelectric devices. How do we convert electricity into heat practically and heat into electricity? But with the understanding of Seebeck effect and Peltier effect, I hope you would be able to understand those kind of devices as well if you encounter them anywhere. Okay. So now let's begin with an interesting topic, that is the quantum dot devices. Before going into that topic, let me quickly remind you that the unit of the charge current is ampere and the unit of heat current is watts. Okay, joule per second essentially. This is coulomb per second, this is joule per second. Please keep this in mind. This is a minor point but an important one. Okay. So now let's begin with the quantum dot devices. A quantum dot device means that the active region of the device now is a quantum dot or a 0D conductor, which means a conductor in which electrons are confined in all the directions. Okay. So it can be a molecule, it can be a nanostructure, a very small nanostructure in which electrons are confined from all the directions, and it can be anything. It's the quantum dot or a 0D material is a very general term, and as all of us know that one of the most interesting features I would say of modern semiconductor industry has been scaling. Scaling means making smaller and smaller devices with better and better performance. And I would say that these quantum dot devices are the ultimate limit of that scaling, because here in these devices we use almost a single molecule as a device, as a channel. So we put a single molecule between the two contacts and that becomes a quantum dot device. Okay, or we can also fabricate semiconductor structures in which the size of the semiconductor in all three directions is few nanometers only. Okay, and that is a quantum dot. So quantum dot is also known as an artificial atom. It's like an atom because the atom is also very small, electrons are confined in all the directions. And because of the confinement of electrons, we always need to deal with the discrete energy levels in these systems. So far we have mostly dealt with 2D channel, 1D channel or 3D channel, bulk materials as well. We did not do a very thorough analysis of 0D channels, and that's what we are going to do now. And in a 0D conductor, the characteristics is that the electrons are confined in all the directions, which means that the electronic energy is discrete. There is no continuum of energies. It's like energy of a single atom. Okay? And this is how the energy levels of a quantum dot or a molecule look like. Okay? So if you recall, in an atom there are atomic orbitals in which electrons reside. Atomic orbitals are allowed electronic wave function in the atom. Similarly, in a molecule or in a quantum dot, we have molecular orbitals. MOs. So electrons in different atoms interfere with each other, and because due to this interference, due to the interference of various electronic wave functions, in a molecule, molecular orbitals are formed. So these molecular orbitals essentially belong to the entire molecule, they do not belong to a particular atom in that molecule. Similarly, in quantum dots as well, we talk about discrete energy levels, and these are the molecular orbitals of the quantum dots. So, once a quantum dot is formed, especially the outer shell electrons, the loose electrons in the atoms, they interact with each other and they form molecular orbitals. And so, these orbitals will have discrete energies because electrons are confined in all the directions, and the electrons will be filled in these orbitals from the bottom, from the lowest energy to higher energy. So, there are several important terms here. One is the molecular orbital, which is the up to which electrons are filled in a quantum dot or in a molecule, is known as highest occupied molecular orbit or highest occupied molecular orbital or HOMO, HOMO. Similarly, the lowest unoccupied orbital is known as LUMO orbital, lowest unoccupied molecular orbital. So, this is the orbital that has energy just above the highest occupied molecular orbital. Okay. So, these two orbitals are extremely important, HOMO and LUMO orbitals. HOMO is the orbital up to which electrons are filled, LUMO is the one which is just above the filled orbitals. And depending on the number of electrons in the system, there might be one electron in the LUMO or there might be two electrons as well. So, as all of us know that one orbital can take at max 2 electrons of different spins. So, this HOMO can take either 1 or 2 electrons. So, generally in most of the cases in stable quantum dots, generally there are 2 electrons in HOMO, because if there is 1 electron in highest occupied molecular orbital, in that case that becomes quite a reactive quantum dot, because it has a tendency to give 1 electron or to take an electron from the external environment essentially. So, generally we assume that, generally in this discussion we assume that HOMO is completely filled, 2 electrons are there of opposite spin. LUMO is completely empty, although in some cases HOMO might be half filled as well. So, it is not that always HOMO is completely filled, but that is the case in most of the situations. Now, there are several terms that we need to understand. The notion of Fermi level is not properly defined in these systems, because there are very less number of electrons in this system, and this statistics of electrons cannot be done properly. However, we define the notion of Fermi level from the basic definition of Fermi function, Fermi level, which is, it is the level, it is the energy level at which the probability of being occupied is half. So, the Fermi level is the level at which the probability of an electron being found is 1 by 2. So, in this case the probability of an electron being found at HOMO level is 1, because it is completely filled. The probability of electron being found in LUMO is 0. So, the Fermi level will be right in the middle of LUMO and HOMO. However, if we have a system in which this is the way electrons are filled. So, in which HOMO has 1 electron and LUMO does not have any electron. In this case, the Fermi level is assumed to be at the HOMO energy level, because HOMO is half filled, highest occupied molecular orbital is half filled, which means that the probability of this state being occupied is half now. So, this becomes the Fermi level of the system. So, this is how we define the Fermi level in quantum dots. We also have a notion of ionization potential, which comes from the atoms actually, this comes from atoms. So, this means ionization potential is essentially the energy that we need to ionize the system, to take out an electron from the system into the free space. And the free space energy of the electron is defined by this vacuum energy level. So, this is the level at which the electron becomes totally free from the system. So, the difference between the vacuum energy level and the HOMO energy is known as the ionization potential, and this is the energy that is required to take one electron out of the system or to ionize the quantum dot or the molecule. Similarly, we have another parameter which is known as electronic affinity, and that is the amount of energy that is released when an electron is occupied or electron is taken by the system, and that is the difference between the vacuum energy level and LUMO energy level, because any additional electron will be taken in LUMO energy level, and the energy that will be released will be the difference between the vacuum energy level and the LUMO energy level. So, that is known as the electron affinity of the quantum dot. The difference between vacuum energy level and HOMO energy level is known as the ionization potential. Okay. So, these are some basic terms, the notion of highest occupied molecular orbital and lowest unoccupied molecular orbital. And if you give a careful consideration, LUMO is like the bottom of the conduction band and HOMO is like the top of the valence band in a bulk material. So, these are quite analog ideas, analogous to each other. So, this is a very brief introduction to quantum dots. Now, in devices, we need to put these quantum dots between two contacts, between the metal contacts essentially. And as usual, these contacts are bulk and metallic contacts. Fabricating these devices is an entirely different method, so we will not go into that here. Generally, we need to grow on top of, so this quantum dot or this 0D material could be an organic molecule as well, or this could be a semiconductor nanostructure as well, and there are different ways to fabricate these different nanostructures essentially. So, how does a contact look like? A metal has a Fermi level EF, and generally what we assume is that all the energy levels up to this Fermi level are occupied, which means that metal has lot of electrons and all the energy levels up to this level are filled. So, electrons are there in surplus up to this energy level. Metal has additional electronic states as well, even above the Fermi level, but those are empty states. So, these states are empty, above the Fermi level are empty. Okay. And the energy required to take out an electron from the metal to vacuum, which means to free an electron, is known as the work function. So, the difference between the vacuum energy level and the Fermi level is the work function of the metal. That will also be the ionization potential of this metal in a way, because that is also the same amount of energy, because if this metal takes an extra electron in it, the energy that will be released will be this vacuum energy level minus the Fermi energy level, and this is known as the work function, which is essentially the difference between the vacuum energy level and the Fermi level. Okay. So, just to summarize, the contacts are metallic contacts, these are bulk contacts, they have lot of electronic states, there is a continuum of electronic states in a way, and up to this energy level the Fermi level, all the electronic states are filled, and above this energy level all the electronic states are empty. So, that's a key point here, and that's what we need to keep in mind. Okay. So, that's a very general model of the contact, and just to quickly remind you, a general model of a quantum dot or a nanostructure or an organic molecule or any general structure that is in which electrons are confined in all the directions is this, in which we have molecular orbitals, and these orbitals are occupied by electrons in the order of increasing energy. The highest occupied molecular orbital is known as the HOMO orbital, the lowest unoccupied is known as the LUMO orbital. And depending on the occupancy of HOMO, the Fermi level can be defined in these systems. Now, while making a device, we need to put this contact in touch with the quantum dot. Generally, this is the way we symbolize a quantum dot or any organic molecule, or just this symbolic representation. This actually means an organic molecule, but this means any nanostructure in which electrons are confined in all directions. So, so what happens when we put a metallic contact in touch with this molecule or quantum dot? So, on one side, on the metallic side, electrons have this kind of energy profile. On the right side, in the molecule, in the quantum dot, electrons are like this. On the left side, they are in a continuum of energy, and the occupancy is governed by the Fermi level. On the right side, they are in discrete energy levels, and occupancy depends on the number of electrons in HOMO and LUMO orbitals. Okay. So, it is interesting what happens when these two are combined. When we put a quantum dot in touch with a metal, in equilibrium, what happens is, when a metal is connected to the molecule, first of all, equilibrium should establish. Equilibrium means very soon electrons will rearrange themselves across this metal and quantum dot in such a way that there is no net current in the system, which means that the Fermi levels of both the systems are aligned to each other. So, that is the first basic thing that happens whenever we put any two materials in contact with each other. What happens is, very soon equilibrium is achieved, and in equilibrium a uniform Fermi level must be established between both the materials. The interesting thing happens when the Fermi levels are different in isolated contact and quantum dots. Now, we need to understand how this equilibrium is obtained, how the electrons will rearrange themselves in such a way that there is a uniform Fermi level across the metal, across the contact and quantum dot. And as expected, electron rearrangement needs to happen in order to do that. Okay. So, the Fermi levels actually change with addition or subtraction of charges, and equilibrium is obtained. Equilibrium means that both the Fermi levels need to be aligned. So, which means that now we need to have a rearrangement of charges between the two systems, between the metal and the quantum dot or the molecule, and the Fermi levels depend on the, if you remember, the Fermi levels actually depend on the applied voltage as well. If you remember, in our two terminal device, if this is the left contact, this is the right contact, and if we apply a voltage V here and the left contact is grounded, the Fermi level on the left contact is EF1, the Fermi level on the right contact is EF2, then EF2 will be EF1 minus Q times V. So, any voltage that is applied across the system will change the Fermi level as well. So, what it means is, if there is or in other words, if we deposit a charge here, because of the voltage difference, the Fermi levels will be changed. Also, from quantum statistics, the position of the Fermi level depends on the number of electrons in the system, because if the number of electrons in a quantum dot, let us say if we have a quantum dot whose molecular orbital are organized in this way, if the number of electrons in this system are just 5, this becomes the HOMO orbital and this becomes the LUMO orbital, and the Fermi level lies at HOMO. On the other hand, if the electrons in this system are 6, the Fermi level lies between HOMO and LUMO. So, this Fermi level, apart from the electrostatic voltage, the Fermi level also depends on the number of charge carriers or number of electrons in a particular system. Okay. So, there are two factors. So, this is a very subtle point. I would like to remind you that the Fermi level, the position of the Fermi level depends on two factors. One is the electrostatic voltage, second is the number of electrons in a system. Generally, in large systems we do not, or we ignore the dependency of Fermi level on number of electrons, because number of electrons are already huge. So, adding 1 or 2 electrons does not make any significant difference there, and moreover as we will see that there is a role of density of states as well. So, if the density of states is significant, in that case this number of electrons does not make much impact here. But there are 2 points that we need to keep in mind, that the position of Fermi level depends both on number of electrons and the charge or the electrostatic voltage. So, whenever any electron rearrangement happens in the system, whenever we put a metal in touch with a quantum dot, electrons are transferred from one system to another system, let us say, then the number of electrons change in the system, as well as there is an electrostatic voltage that appears, electrostatic voltage difference that is also produced. So, both of these needs to be taken into account, especially in quantum dot devices. So, that is a subtle point. I would like to repeat it again, that the Fermi level position depends on the electrostatic voltage, and that depends on the amount of charge that is present, or if we have applied a negative voltage or a positive voltage on certain terminal. It also depends on the number of electrons, because it is the Fermi level is also the chemical potential of the system. It is also a function of the number of electrons in the system in equilibrium. And if the number of electrons change, then both of these factors change. Both electrostatic voltage change across the system, because electrons are now getting transferred from one system to another system. So, there is a positive charge is being produced at one place, negative charge is getting accumulated at another place. So, there is this electrostatic voltage difference that appears across the system. Also, since the number of electrons are changing in the quantum dot, just by the number the Fermi level might also change. So, Fermi level will change because of two factors. One is because of the charging, because of the electrostatic effect, and second is because of the number effect, which is known as the state filling effect, because if we fill this HOMO state, this Fermi level changes significantly, even if there is no applied voltage in the system. So, these are termed as charging effect and state filling effects. So, let us first consider the what is known as the state filling effect, which means how does the Fermi level depends on number of electrons in a system. Because whenever we put a metal in touch with a quantum dot, the number of electrons will change in both the systems. So, we need to first understand how is the number of electrons govern the Fermi level, and this is the notion of charging of the molecule, and from here the idea of quantum capacitance and electrostatic capacitance actually comes up. So, quantum capacitance is essentially, this idea comes from the dependence of the Fermi level on the number of electrons in a system. Okay. So, let us see where it comes from. Under equilibrium, the Fermi level in metal molecule system, metal quantum dot system must be uniform, and in order to achieve that uniform Fermi level, certain amount of charge needs to be transferred across the system, sometimes if the Fermi level are not aligned before joining them. And it's also possible that only a fractional amount of charge is transferred. What it means is that it may not be necessary that entirely a full electron is transferred to the from metal to the quantum dot. It might happen that the electronic wave function is now such that part of it is on metal and part of it is on quantum dot. So there is a non-zero probability of a certain electron being found both on the metal contact and the semiconductor quantum dot or a molecule. So that way we can say that only a fractional amount of charge is transferred, and sometimes that's also the case. Okay. So we will consider the case in which delta n electrons are transferred from the contact to the molecule. Okay. If delta n is plus 1, which means that one electron is transferred from metal to the quantum dot, and in that case LUMO will be half filled if the HOMO was already fully occupied, and that's what we assume, and that's why the Fermi energy or the Fermi level will now be at LUMO level. Similarly, if delta n is minus 1, which means one electron is transferred from quantum dot to the metal, in that case there will be only one electron left at the HOMO orbital, and the Fermi level will now be at HOMO energy level. So that way Fermi level changes as a function of number of electrons. In general, let us say in general the total number of charges on a molecule is given by this relationship, which is a fundamental relationship. So the number is given by density of states times the Fermi function and integrated over all possible energy values. So if we take this EF to be the equilibrium Fermi function, which means this is the Fermi function after joining the metal to the quantum dot, in that case this number will be the number of electrons in the system at equilibrium after the molecule is in touch with the metallic contact. So in order to understand the effect of charge transfer on the Fermi level, we essentially need to calculate this quantity. How does the Fermi level changes with respect to the change in charge? And this will come from this relationship, which is the relationship between the number of electrons to the Fermi function. So if we take a derivative or generally in most of the systems the derivative will be taken a little later. Most of the systems, for example in metals, only the states up to the Fermi level are occupied. So this integration is taken only up to EF, and up to EF this Fermi function is 1. So n can be rewritten as this. Fe becomes 1, and instead of plus infinity it becomes the Fermi level. The reason we can write it like this is that generally the Fermi level of the metal does not change with the number of electrons, because there are already a lot of electrons in the metal. So even if few electrons go to the contact or few electrons come from the contact, the Fermi level does not change much, and generally the equilibrium Fermi level is at the Fermi level of the metal, and that's why this integration limits boil down to this level. Now if we take the derivative of this with respect to EF, dN by dEF, this is what we obtain. This is the density of states at the Fermi level, or delta EF becomes delta n times GEF, and this is what I would like you to think about. This is the change in the Fermi level when we change the number of electrons in the system by delta n, and this depends on the density of states of electrons at the Fermi level. So the density of states in electrons is quite huge, so that's why delta EF is almost 0. but in quantum dot systems or in nanostructures, density of states is not much, and in that case delta EF is significant as a function of delta n as well. So that is why this change in the Fermi level as a function of the number of particles, this is especially important in nanomaterials, in quantum dots especially, in which the density of states is very small. And from here comes the notion of quantum capacitance. So the quantum capacitance is defined as q square times the density of states. So we will come back to this idea of quantum capacitance in the next class, where it comes from. So if we define it like this, in that case delta EF becomes q square times by CQ times delta n, and this is a very important relationship for quantum dots. So we will stop here, but the takeaway from today's discussion on quantum dots is that the Fermi level of quantum dots or nanostructures, it depends on both the number of electrons and also the electrostatic voltage that is applied across the system. Okay? And first we are just considering the impact or the effect of number of electrons on the Fermi level, and here comes the notion of quantum capacitance, with which we will begin our next class. Okay? So thank you all and see you in the next class.